Alright, good afternoon, Algebra 2. Today we're going to be talking about 7.2, which is properties of powers. So this is how we're going to be able to operate with all the powers that we're going to see throughout the rest of this chapter. So here we have a table of all the different types of situations you could find yourself in when you're doing operations with powers. So we have all these postulates over here, what we're going to do with them, and then just a little example using variables here of each one. Now each of these you should have seen before. We've learned these in Algebra 1, but let's go ahead and review. That's what this little section's for in this unit, so that you know how to use these properly. So our first postulate is your product of powers, meaning product, if you remember, is when we multiply, we're going to multiply two things that have powers on them. So we're going to multiply our bases, that means we add our powers. So over here in our example, notice your bases are the same. Doesn't matter what they are. Here they're b's, and your exponents are different. So what you would do with these is you would just make it to the same base, and then you would add the powers together. So we're multiplying our bases, we add the powers. So therefore, if this was b squared times b to the fourth, then it would be b to the 2 plus 4, which would give us b to the 6th power over here. So you would just add them together. Now when we have a power of a power, that means we're going to take one power to another power. So if you look at the setup over here, you have b to the m to the nth, meaning you have two exponents here. So that means when you take a power to a power, you're going to multiply your powers. So for instance, if this was b squared, and then we take it to the 4th power, let's say, so b squared to the 4th, you'd multiply your exponents. So you would have 2 times 4, which is going to give you 8. So b to the 8th power now. Our next property or postulate is going to be your power of a product, meaning you have two things in here being multiplied and you're taking their power. So what that means is if you have a product to a power, that means you're going to take a power and it's going to go to each base in here. So it's kind of like the reverse distributive property if you want to think of it that way. So each element in here gets hit with this m. So it becomes a to the mth, b to the mth. So for instance, if this was ab squared, then it would become a squared, b squared. Next postulate we need to talk about is your quotient of powers. And quotient, remember, means to divide, so we're going to be dividing our bases, which means we subtract our powers. So for instance, it's going to look like this. So you have b to the m over b to the nth power, and so that means you're going to subtract these. It's the opposite of multiplication, which makes sense, because that's what division is. It's the opposite of multiplication. Well, guess what? Subtraction is the opposite of addition, which is what we had up here. So you're just going to take b to the m minus m. So for instance, if this was b to the 5th power divided by b squared, this would become b to the 5 minus 2, which is b cubed, is what you'd end up with here. Your next quotient is your your postulate is your power of a quotient, meaning you're going to have some division in here taken all to one power. It's just like your power of a product. Whatever you have in here has to get hit with that m. So here we get a to the mth and b to the mth. We're just dividing them now. So a quotient to a power is a power goes to each base again. And the last postulate is probably the simplest one to remember, but easily the one most of us forget, is anytime you have a 0 exponent. Anything to the 0 power is going to give you 1. Anything. b to the 0 is 1. So if I put anything I wanted in here for b, it could be 8 to the 0 power is 1, x to the 0 power is 1. Anything to the 0 power is going to give you 1. So that's just a rule you kind of have to live by. Something to remember here. Alright, so example 1 says, a multiple choice test is 2 pages long. Each question has C possible choices. Page 1 has 5 questions. Page 2 has 8 questions. How many different ways can students answer the questions? Now if you remember from our first video, we did sort of a setup of this same kind of thing here, and we listed out each question and then their probabilities. Well, we don't have probabilities this time. We just know that each question has C different ways to answer it. So remember, if we had a 5-question quiz, we wrote out C 5 different times. Now we're not going to do that because we know we ended up with it to the 5th power because we had C 5 times over. So here we're just going to say C to the 5th power, and that represents your whole first page because there's 5 questions. C different ways to answer them. You would have C times C times C times C times C, or C 5 times. So that's only page 1. Page 2 has same amount of choices for each question, so C again, but page 2 has 8 questions on it, so now we have C to the 8th power. So again, that would be C times itself 8 times. Now they want to know how many different ways can students answer the questions. They mean all the questions here. So what we're going to do is we again have to multiply. So c to the 5th times c to the 8th power. Well, we know when we multiply bases, we add the exponents. So we have c to the 5 plus 8, giving us c to the 13th power. Now again, we do not know how many choices we actually have. That's why it's just represented by the letter C. So how many ways can the students answer the questions? It would just be c to the 13th ways. Alrighty, example 2 just says to simplify x to the 2nd all to the 5th power. Now remember, this is our power to a power rule here. So all you need to do then, if we're taking a power to a power, that means we multiply these two numbers. So 2 times 5 gives us x to the 10th power. And that's as simple as we can get, so that's all it is. So x to the 10th power. Next example, example 3, says simplify 3d over e all to the 4th power. Now we have a lot of things going on in here. We have a product of 3 times d in the top. We also have a quotient of 3d divided by e. Now you can use these rules in conjunction with one another. The main thing is that you need to make sure you pay attention to is that everything in here is being taken to the 4th power. So everything in here needs to get a 4th power. So let's rewrite this. We're going to do this in 2 steps here. So we have 3 to the 4th power, and then d to the 4th power, because these are 2 separate entities. So d to the 4th power as well. And then over, and now everything's staying in its place right now, but they all now have their own individual 4, which is exactly what we wanted to happen here. Now, can we simplify this a little further? Absolutely. Now, d and e you can't really do anything with because, well, what is d to the 4th? We don't know what d is, so we can't take it to the 4th power. Same with e, can't really do it. But I could take 3 to the 4th power. Now, you might be thinking, oh, I'm multiplying these, so let's add these together and get 7. No, 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 no. These are not bases. These are 2 separate things. We have a base of 3 to an exponent of 4. So anytime you just have a real big number 3 out here, you just treat it like normal. So this is literally just, well, let's turn this on here, 3 to the 4th power. So then you have to enter, and that gives us 81. So 81 is really what we get here. 3 to the 4th is 81. And then we still have d to the 4th power. And over e to the 4th power. And like I said, can't do anything with d and e. If these matched, we could do something with them, but since they're 2 separate variables, that's all we can do, is 81, d to the 4th, e to the 4th. Alright, we're getting a little sticky in things here. We got a lot of stuff going on here, so let's take it one step at a time. That would be my biggest piece of advice for you. Just take it one step at a time, write it out, very simply follow it rule by rule. And then once we get better at it, we can get into more complicated ways of doing things. Alright, so let's take a look at our first, our numerator here, see if we can simplify that at all. I can't really combine anything because I have x's and y's, so those are not like terms. And then this 4 is all by itself. Let's just pull the 4 out front because I like to have my coefficients first and then my variables. So I'll have 4x cubed, y to the 9th power. And then downstairs, again, 8x to the 7th times y to the 4th. Can't really do anything with that. So I'm just going to keep my coefficient out front and then keep them in the same order. We always go alphabetically, just so you know. X to the 7th, y to the 4th downstairs. Okay. Now I can't do anything with the numerator individually and the denominator individually, but I might be able to do something combining the two. As you notice, we have x's together and y's together. We can do some of them with those. But furthermore, we also have the fraction 4/8. Now 4/8 we know just reduces to 1/2. So let's just go ahead and reduce that right off the bat. I'll put 1 upstairs, and then I'm probably going to have more stuff over here, so I'll make a big fraction bar. And then 1/2. It's 4/8 is 1/2. Now those are just simple numbers. We treat those normally like we would. Now here, this isn't 3/7. This is x to the 3rd over x to the 7th. Now when you do this, let's think of the easiest way to do this. You're going to subtract. And that means that you're going to have, well, if we do 3 minus 7, that's going to be -4. So what happens is we have x to the -4th. We haven't really addressed negative numbers yet, so if you end up with a negative, just for all intents and purposes right now, just put it downstairs. So x to the third over x to the seventh, we do 3 minus 7, which is x to the negative fourth. We drop the negative and just put it downstairs. Okay, we will address negative exponents, I promise you. But just for now, if it's negative, we know that goes down below, so just put that downstairs. Okay, so that takes care of our x's, so those are done. I like to also just cross stuff out as I work, just so I make sure I don't hit it again. All right, now we have y to the 9th over y to the 4th. That means if we're dividing our bases, we subtract our exponents. So we get y to the 9 minus 4, so y to the 5th, and that's a positive, so I end up with that guy upstairs. So 1y to the 5th, and then x to the 4th. Now how do you know you're done? Well, check your coefficients. 1/2 does not reduce anymore. And then also x and y are two separate variables. We cannot combine those two. So since that's all I have left, I am done. The only thing I might recommend doing here is getting rid of this one. This is a matter of personal preference. I think it's redundant to put the 1. You can keep it if you'd like, but I would rewrite this guy as y to the 5th over 2x to the 4th and leave it at that. If you have the 1 in there though, that's not wrong. That'll work for us. Okay, so there is our answer for this guy. All right, let's take a look at our next example, number 5 here. It says on average, Earth is about 150 times 10 to the 6th power kilometers from the sun. Light travels at about 3 times 10 to the 5th kilometers per second. About how long does it take light from the sun to reach Earth? So they give us a hint here. It says use the formula T equals D over R. Now if you notice, our numbers here are in scientific notation. So we're just going to be able to now, since we now know about powers, we're going to be able to work with those numbers. All right, so we're going to use this formula T equals D to the R, which is just time equals distance over rate. So we have our distance. It's 150 times 10 to the 6th kilometers. That's on average. The Earth is about that far from the sun. So that's going to go where our D is here. So we have T equals, they want to know the time, about how long. That's going to be a unit of time. So we know that's not going to give it, not going to have a unit yet. Our distance is 150 times 10 to the 6th. And you could put the units in here, but we know that we're going to end up with seconds. So the kilometers are just going to cancel out. Downstairs then, it says light travels about 3 times 10 to the 5th kilometers per second. So that's its rate. It's traveling at that speed. So we have 3 times 10 to the 5th power. And then kilometers per second. So now, we don't want to leave our answers like this. We actually want to figure out what we're dealing with here. So you treat this just like you normally would. Now, I treat scientific notation numbers separately. I deal with their the first part, which is actually tells you the value of the number, together, and then I deal with their exponents separately, because these are always going to have a base of 10. That is the base behind scientific notation. So those we're going to use our exponent rules. 150 over 3 is just 150 over 3. Well, what's 150 divided by 3? Well, that's 50. So that comes out as an even number. That's nice there. So 50 times, now when we work with exponents, our bases don't change. So 10 is still going to be there, but then we know we're dividing our bases. So what do we do with our exponents? That's right, you're going to subtract them. So 6 minus 5 would be 1, and that's a positive 1, so we know it goes up with the 50. So 10 to the 1st, which is just 10. We all know that. So 50 times 10 gives you 500. Whoops, 500. 500, and we know our unit is going to be seconds. So 500 seconds to reach Earth, which might seem like a long time, but 500 seconds, first of all, really is not that long. And think about how far it has to travel. So that's actually pretty impressive here. All right, we have one more example, so I'm going to have to save that for the next video just because we are running out of time here. So bear with me and we'll load up in the next video. Thank you.